The next one is a classical example of a problem where linear algebra plays an important role in understanding. This is an economic supply and demand problem, also known as a Leontief model, for an economist who I believe won a Nobel Prize in economics for his work in this area. The idea is that we break an economy into sectors, commodity areas, and think about what are the costs in terms of materials from other sectors and for the sector that we're interested in are required to produce that material. Right? So, for example, to produce $1 million worth of energy might require $0.1 million worth of metal, $0.3 million worth of transportation, $0.1 million worth of construction materials and labor, and $0.3 million worth of input energy, right? And if you expend that, you get a gross output, not a net output, of 1 million output of energy. Similarly, to produce 1 million of metals requires 0.3 million of energy, 0.2 of transportation, 0.2 of construction, 0.1 in metals. To produce or provide $1 million worth of transportation requires 0.2 of energy, 0.5 million of metals, 0.2 of construction. And to produce construction materials and product, worth 1 million requires 0.2 million of energy, 0.1 of construction, 0.4 of transportation, 0.1 of metals. These are essentially the inputs that are required from various sectors to create output from that sector. In addition to the requirements between the sectors, that to produce energy needs metal, needs transportation, construction, and other energy, and so on, there's also what we might call internal demands to the economy. There's also external demands, which we might term consumer demands. Outside of the generation economy, there is an interest in energy, an interest in construction, interest in transportation, and so on. And so if consumer demand was for $80 million worth of energy, 50 million of construction, and 100 million of transportation, with no consumer demand for raw metal, how much must each industry produce to satisfy both the consumer demand and the demands from all of the sectors that are sort of needed to produce that material? How do we write down a model for this? Start with the variables. Right? Variables are the unknown parts. In this case, the unknowns kind of have two pieces. The supply, how much is being produced, and the total demand, how much is needed, right? For each of these different sectors of the economy. Let's use X's for supply, X1, 2, 3, and 4 for the total supply of energy, metals, transportation, and construction. And let demand, total demand, be D1, 2, 3, 4 with the same ordering. Be very careful here about the matching of subscript numbers to the sector when constructing this, right? Especially since you're never sure whether the ordering in the words is going to be consistent with how you've written down your variables. Once we have variables, we can write out our system of equations. We're going to have one equation for every sector and write out the total demand as a variable, D1, D2, D3, D4, and so on, And on the right-hand side, we're going to write the total demand kind of as calculated from the total supply. So what is the total demand for Sector 1? Well, there's demands from 4 different sources, plus a consumer demand. So what's the demand for 1? Remember, 1 was of demand for energy. The demand for energy partly comes from production of energy. To produce a million, if we are producing $1 million worth of energy, or however many millions of energy, x1, each $1 million worth requires 0.3 of energy, so there's a demand of 0.3 times x1 here. For every million of metals, we need 0.3 million of energy. So we have 0.3 times x2 as a demand of energy. For every million of transportation, we need 0.2 million of energy. So there's a demand of 0.2 x3 here. And for every million of construction materials, x4, there is also a 0.2 million demand of energy. So there's a 0.2 x4 demand here. In addition, there's a consumer demand of 80 million. So we have an extra demand of 80 million. These are all of the demands for energy, one for the production of each sector, and a final one for the consumer demand. We do the same thing for each sector. For metals, there's a demand of 0.1, to produce energy, there's a demand of 0.1 of metals. To produce metals, there's a demand of 0.1 of metals. To produce transportation, there's a demand of 0.5 of metals. To produce construction, there's a demand of 0.1 of metals, and there's no consumer demand. For transportation, to produce energy, there's our demand for 0.3 of transportation. To produce metals, there's a need of 0.2 of transportation. To produce transportation, it does not require transportation. So 0. To produce construction materials requires 0.4 of transportation. There's a demand for 100 million. For the final piece, construction, to produce energy requires 0.1. To produce 1 million of metals requires 0.2. To produce transportation requires 0.2. And to produce 1 million of construction requires 0.1 of additional construction materials. A $50 million consumer demand added to that. This is our now system of equations that describes the problem. What would we like to do? We would like to find a consistent solution. That is, where the total supply is exactly equal to the total demand. The amount that we're producing, x1, x2, x3, x4, is exactly equal to how much we need, both to produce that and to satisfy consumer demand. Why would we want to do this? Well, we want to produce at least, if we produce less than that, then we can't satisfy all of the demands. The economy cannot run sort of at the level it wants to, in a sense, because there is not enough being produced by at least one sector. But to produce more would be inefficient. you're producing more than there is a need for. Maybe under some circumstances you might sort of want to stockpile, but in some cases that in a sort of a formal sense, that desire ought to be sort of part of the so-called consumer demand. So even there, that kind of doesn't really work. Right? It'd be wasteful to produce more than can actually be used. At least to a sort of a first approximation. So what we would like to find is a set answer where this left-hand side is in fact equal to these same x's over here. How can we do that? There's actually a couple of ways. One way is to stick the x1s into this situation, of the x1, x2, x3, x4, try to rearrange that and solve for it. That becomes very messy. There's not a sort of an easy way to know how to start with that. Another is a so-called recursive approach. Make a guess what the sort of supply should be, x1, x2, x3, stick those into these equations and calculate what would the demands be. The demands will usually be larger than that input. Maybe not always, but usually. Then use those new demands to say, well, if I wanted to get that demand, what would I need to produce? So take those new demands and plug them in as the new x1s. So basically make a guess, calculate the d's, and then say that those d's must be equal to the x's. Plug those new x's in, calculate new d's, and so on. And if you do this, it turns out that at least with reasonable parameters in the model, reasonable coefficients, you'll get an answer eventually. Right? What is, so again, this recursive solution? We're going to use this model, guess an initial set of supplies, compute the demand, use these the new supplies, keep doing this. The initial guess should be at least as big as the consumer demand, because we know that's a lower limit of what we need. It should probably be more than that, because we know we're also going to need stuff to satisfy the sectors producing what they have. But there's not really a well-defined best way of guessing. One possible way of starting a guess is just to double the consumer demands and go from there. Right? If we do that and we stick our initial guess in, double the consumer demands and calculate the new values, this is actually something that we can do by hand, and we would get new demands of 188, 126, 188, and 116. The guess is not very close to actually the demands we get. In particular for this second sector, because we had a consumer demand of 0, we guessed 0, it turns out as being 126. Huge difference. Some of the demands that we calculate are a little bit bigger. 188 is more than 160. Some are a little bit less. 188 is less than 200, and so on. But we're obviously nowhere close to our initial guess, so we would repeat. We would take these answers and we would plug them in again. We could probably do one more step by hand with a calculator. It already starts getting messy. If we do that, we get a new set of demands. We're still pretty far away. If we look at our first sector, our demand is 235. Our guess was 188. This is a 25% error, right? Not very good. Even the best error, an error of 25% and an error of 23%. Some of them are a little bit better. This is not too far off, but we have big errors, so we would need to repeat. Already our numbers are starting to get messy. We would really not want to keep doing this by hand. And so again, just to get you a sense of how this would play out, we can do this computationally. If I calculate 1, 2, 3, 4, 5, 6 steps, right? If we only compare the change, and we ask between 5 and 6, how much are things changing? A little bit less than 300 to a little bit more, a little bit less than 200 to a little bit more, to close to 280, a little bit more than 290, about 175, about 190. These numbers look fairly close. The errors are less than 10% as a one-step difference, but they're not super close. And in fact, if we were to keep going and we did another 10 steps or another 20 steps, we would actually find that although the single step error here is less than 10%, we are still very, very far from a correct solution, right? If we were to stop here, we would have errors almost 30% of the best answer, right? Stopping after 10 steps, we're still pretty far off. After 20 steps, we're not too bad. After 20 steps, if we compare to, say, the 100th step, we're within less than 10 for all of our answers. Actually, the percent error is within 2% here. After 50 steps, we have pretty much gotten the right answer, less than a 0.01% error. But that's 50 steps. We're never going to try to do this without a computational infrastructure. Right? We do want to phrase this back into the language of the original problem. We did get an answer, not by hand, but we did get an answer. The final answer is that the energy industry must produce about 420 million. The metal industry must produce just under 290 million. Transportation must produce about 380, and construction about 250 in order to satisfy those consumer demands. I really want to emphasize that this iterative, this recursive solution does not play well with hand calculation. Right? We could, as an alternative, have rewritten the system where we replace the left-hand side with the desired output of setting these two things equal. We want to find values of x1, x2, x3 that satisfy all of these equations. Maybe we can get there by algebraic manipulation, but this is now a system with 4 unknowns and 4 equations. It's not obvious even where we really begin here. And you can certainly imagine that for larger problems with even more variables, it would not be a reasonable approach. Really, what we need to answer this question are the tools of linear algebra.